The historical discovery of the planets, a journey through time and space. Settle in, dear listener, and let yourself relax. Close your eyes if you wish, and allow your mind to drift back through the centuries to a time when the night sky held mysteries beyond imagination. Tonight, we journey together through the remarkable story of how humanity discovered the planets, those wandering lights that puzzled our ancestors and inspired generations of stargazers to look upward with wonder. The ancient watchers, long before cities glowed with electric light, before telescopes revealed distant worlds, our ancestors looked up at the night sky and saw something extraordinary. Among the thousands of fixed stars that held their positions night after night, season after season, there were a few peculiar lights that moved. The ancient Sumerians, living in Mesopotamia around 3000 BCE, were among the first to carefully track these wandering stars. They noticed that while most stars formed unchanging patterns, the great celestial tapestry we call constellations, 5 bright objects, drifted slowly through the zodiac, taking their own paths against the starry background. These weren't stars at all, though they didn't know what else to call them. Imagine yourself as one of those ancient observers standing atop a ziggurat in the warm Mesopotamian night. The air is still and clear. You've climbed these steps countless times, and you know the sky as well as you know the streets of your city below. There, that bright point of light near the moon, it wasn't there last week in quite that position. You make a mark on your clay tablet, noting its location among the fixed stars. You are participating in one of humanity's oldest sciences, though you wouldn't call it that. You are simply watching, recording, trying to understand the heavens. The Babylonians inherited this tradition and refined it. By 1000 BCE, they had identified all 5 of the visible planets: Mercury, Venus, Mars, Jupiter, and Saturn. They didn't call them by these names, of course. These were names that would come later, bestowed by the Romans. But they knew these lights were special, different from the stars, and they watched them with devoted attention. These ancient astronomers noticed patterns. Venus, the brightest of all, appeared as both a morning star and an evening star, never straying far from the sun. Mercury was elusive, always close to the horizon, appearing briefly at dawn or dusk before vanishing in the sun's glare. Mars had a distinctive reddish hue and occasionally performed a strange backward loop in its journey across the sky. Jupiter moved steadily and majestically through the zodiac, while Saturn, the slowest, took nearly 30 years to complete one circuit of the heavens. The Babylonians believed these wandering stars were gods or the dwelling places of gods, and they associated them with deities in their pantheon. They kept meticulous records of their movements, not merely out of curiosity, but because they believed the planets influenced events on Earth. This was the birth of astrology, inseparable in those days from what we would call astronomy. The Greek philosophers and the birth of planetary theory. Let us drift forward now to ancient Greece, where philosophy and rational inquiry began to transform how humanity understood the cosmos. The Greeks inherited astronomical knowledge from the Babylonians and Egyptians, but they did something remarkable with it. They asked, why? Around 600 BCE, the Greek philosopher Thales of Miletus proposed something revolutionary. Perhaps natural phenomena could be explained by natural causes rather than the whims of gods. This shift in thinking, subtle as it might seem, opened the door to scientific reasoning about the heavens. The Greeks adopted the Babylonian planetary observations but gave the planets new names, associating them with their own deities. The brightest became Aphrodite, goddess of love, later renamed Venus by the Romans. The red planet became Ares, god of war, later Mars. The largest and most majestic became Zeus, king of the gods, later Jupiter. The slow, distant wanderer became Kronos, father of Zeus, later Saturn. Swift Mercury kept a similar name in both traditions, representing Hermes, the messenger god. But the Greeks wanted to understand more than just where these planets appeared in the sky. They wanted to understand how the cosmos was organized, what kept the planets moving, why they wandered while the stars remained fixed. Picture yourself now in ancient Athens, perhaps around 400 BCE, listening to the philosopher Plato discuss the heavens with his students in the academy. The olive trees rustle softly in the evening breeze. Plato suggests that the planets move in perfect circles because the circle is the perfect shape, and the heavens must surely embody perfection. He imagines a cosmos arranged in crystalline spheres, each planet embedded in its own transparent sphere, all rotating around the Earth at the center. It's a beautiful vision, orderly, mathematical, harmonious, and it almost fits the observations. Almost. But there's that troubling retrograde motion, the way Mars occasionally seems to slow down, stop, move backward for a while, then resume its forward path. How could perfection produce such irregularity? Plato's student Aristotle elaborated on this model, creating a complex system of 55 interconnected spheres to account for all the planetary motions. It was ingenious, if unwieldy, and it placed Earth firmly at the center of everything, which seemed only natural. After all, we feel no motion. The ground beneath our feet is steady. Surely it is the heavens that move, not us. But not all Greek philosophers agreed. Around 270 BCE, a remarkable thinker named Aristarchus of Samos proposed something that would have seemed absurd to most people of his time. What if the Earth and planets actually orbited the Sun? What if the daily rising and setting of the stars was caused by the Earth spinning on its axis? Aristarchus had noticed that his sun-centered model could explain retrograde motion quite naturally. When Earth, moving faster in its inner orbit, overtakes an outer planet like Mars, the outer planet appears to move backward against the stars, the same way a car you're passing on a highway appears to drift backward relative to distant objects. But Aristarchus's idea was too radical. It required accepting that the Earth moved, which contradicted our everyday experience. It required accepting that the stars were unimaginably far away, so far that our orbit around the Sun caused no apparent shift in their positions. Most scholars rejected it, and the idea lay dormant for nearly 2,000 years. Instead, it was the model of Claudius Ptolemy, developed around 150 CE in Alexandria, that would dominate astronomical thinking for the next 14 centuries. Ptolemy kept Earth at the center but added an ingenious mathematical device to explain retrograde motion: epicycles. Each planet moved in a small circle whose center moved along a larger circle around Earth. By carefully adjusting the sizes and speeds of these circles, Ptolemy could predict planetary positions with impressive accuracy. The medieval keepers of knowledge. Let your mind drift now through the centuries that followed, through the fall of Rome and the rise of new civilizations. The ancient Greek astronomical texts might have been lost entirely if not for the scholars of the Islamic Golden Age. From the 8th to the 14th centuries, while Europe struggled through what we call the Dark Ages, astronomers in Baghdad, Cairo, Damascus, and Samarkand preserved and expanded upon Greek astronomical knowledge. They translated Ptolemy's great work, the Almagest, into Arabic and built observatories where they made observations of exquisite precision using massive instruments of brass and wood. Imagine a warm night in 9th century Baghdad. In the House of Wisdom, a great library and research center, astronomers gather to observe the planets. They have refined Ptolemy's tables, making them more accurate. They have named many stars' names we still use today, like Aldebaran, Altair, and Betelgeuse. They have measured the length of the year to within minutes of the modern value, using no tools but their eyes, protractors, and mathematical genius. These Islamic scholars didn't merely preserve Greek knowledge, they questioned it, tested it, and improved it. Al-Battani, working around 900 CE, made observations so precise that his measurements of the solar year and the inclination of Earth's axis weren't improved upon for centuries. Ibn al-Haytham, in the 11th century, began to question whether Ptolemy's crystal spheres could really exist, laying groundwork for a more physical understanding of the cosmos. Meanwhile, in medieval Europe, knowledge of the planets slowly filtered back through translations from Arabic to Latin. Scholars like Thomas Aquinas in the 13th century worked to reconcile Aristotelian cosmology with Christian theology. The 7 moving lights in the sky, Sun, Moon, Mercury, Venus, Mars, Jupiter, and Saturn, were organized in a beautiful hierarchy, with Earth at the center of God's creation. But questions lingered. Careful observers noticed that Ptolemy's predictions weren't quite perfect. The planets didn't always appear exactly where the tables said they should be. Small errors accumulated over the centuries. Something wasn't quite right about the model, elegant as it was. The Copernican revolution. Let us move forward now to the early 16th century, to a cathedral town in Poland, where a church administrator named Nicolaus Copernicus is about to reintroduce an ancient idea whose time has finally come. Copernicus was a careful, cautious man. He had studied mathematics and astronomy at Italian universities, and he was troubled by the growing complexity of the Ptolemaic system. Over the centuries, as observations became more precise, more and more epicycles had been added to keep the model matching reality. The beautiful simplicity had been lost. Picture Copernicus in his tower, late at night, surrounded by books and astronomical tables. He's been wrestling with the mathematics of planetary motion for years. And then, perhaps remembering the old, rejected idea of Aristarchus, he asks himself, what if? What if the sun, not Earth, was at the center? What if Earth was just another planet, orbiting the sun along with Mercury, Venus, Mars, Jupiter, and Saturn? Suddenly, retrograde motion makes perfect sense. It's an optical illusion caused by Earth's own motion. Suddenly, the ordering of the planets becomes clear. Mercury, Venus, Earth, Mars, Jupiter, Saturn, arranged by their orbital periods. Suddenly, everything is simpler. But Copernicus knew how radical this idea was. It meant Earth wasn't special. It meant the cosmos was far larger than anyone had imagined. It challenged religious doctrine and common sense alike. So he worked in private for decades, refining his model, writing his great book, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. The book was finally published in 1543, reportedly reaching Copernicus on his deathbed. It contained detailed mathematical models showing how a sun-centered system could explain the observed motions of the planets. But Copernicus hedged his revolutionary idea somewhat, presenting it as a mathematical convenience rather than physical reality. Still, the seed was planted. Tycho, Kepler, and the music of the spheres. The Copernican model didn't immediately overturn Ptolemaic astronomy. It had problems of its own. Copernicus had retained circular orbits, which didn't quite match observations. What was needed was better data, more precise observations of the planet's positions. And this is where our story takes us to Denmark, to an island called Haven, and to one of the most colorful characters in astronomical history, Tycho Brahe. Let yourself imagine this scene. It's 1576, and on the island of Livin, the Danish king has built a magnificent observatory called Uraniborg, the Castle of the Sky. Here, Tycho Brahe, an aristocratic astronomer with a prosthetic nose made of brass, having lost part of his own in a duel, is conducting the most precise astronomical observations ever made. Tycho didn't have a telescope, it hadn't been invented yet, but he had enormous brass quadrants and sextants, instruments so large and precisely crafted that they could measure the positions of planets and stars to within a fraction of a degree. Night after night, year after year, for over 20 years, Tycho and his assistants tracked the planets across the sky with unprecedented accuracy. Tycho couldn't quite bring himself to accept the Copernican system fully. He proposed a compromise. The planets orbited the Sun, but the Sun orbited Earth. It was an ingenious middle ground, and observationally, it was equivalent to Copernicus's model. But what Tycho really gave to astronomy wasn't his own model, it was his data, the finest set of planetary observations humanity had ever compiled. When Tycho died in 1601, his data passed into the hands of his assistant, a German mathematician named Johannes Kepler. And Kepler, brilliant and obsessive, would use this data to finally unlock the true nature of planetary motion. Imagine Kepler now, working by candlelight in Prague, surrounded by pages of calculations. He's fixated on Mars, that troublesome red planet. Using Tycho's observations, he tries to fit Mars's orbit to circles with epicycles, to circles moving at varying speeds. Nothing quite works. The errors are small, only about 8 arc minutes, a quarter of the moon's width, but they're real, and they're consistent. For years, Kepler struggles. He tries different geometric shapes. Finally, in a moment that must have been both devastating and exhilarating, he realizes the truth. The orbits aren't circles at all. They're ellipses, elongated circles, with the Sun not at the center but at one focus of the ellipse. This discovery, published in 1609 as Kepler's first law, was revolutionary. The circle, that perfect shape beloved since Plato, wasn't how planets actually moved. Nature, it seemed, didn't care about Platonic ideals, but the ellipse worked perfectly. Kepler could now predict Mars's position with unprecedented accuracy. Over the next decade, Kepler discovered his other laws, that planets sweep out equal areas in equal times, explaining why they move faster when closer to the Sun, and that there's a precise mathematical relationship between a planet's orbital period and its distance from the sunday. These weren't just empirical rules, they hinted at some underlying physical principle governing the heavens. Kepler also believed in what he called the music of the spheres, the idea that the planets and their motions created a kind of cosmic harmony, a silent symphony of mathematical relationships. In this, he was perhaps more mystical than scientific, but his laws of planetary motion were rigorously mathematical and would stand for centuries as the foundation of celestial mechanics. Galileo and the telescope. While Kepler was working out the mathematics of planetary orbits, in Italy, another revolution was beginning. In 1609, the same year Kepler published his first law, an Italian mathematician named Galileo Galilei heard about a new invention from the Netherlands, a device using lenses that could make distant objects appear closer. Galileo immediately grasped the potential. He built his own version, improving the design to achieve magnifications of up to 30 times. And then, in the winter of 1609 to 1610, he turned it skyward. Picture Galileo on a clear January night in Padua, peering through his telescope. The moon springs into view, and it's not the smooth, perfect sphere described by Aristotle. It has mountains, valleys, craters. It's a world, rugged and real. He sketches what he sees, creating the first telescopic drawings of another celestial body. Then he turns to Jupiter, that bright planet moving through the winter sky, and he sees something that shouldn't be there according to any model of the cosmos. Tiny stars in a line near Jupiter, visible only through the telescope. He watches them night after night and realizes they're not stars at all. They're moons, 4 of them, orbiting Jupiter just as, in the Copernican system, the planets orbit the Sunday. This discovery, announced in his book Sidereus Nuncius, The Starry Messenger, in 1610, was profound. Here was direct evidence that not everything in the cosmos orbited Earth. Jupiter had its own system of worlds circling it. If Jupiter could have moons, then perhaps Earth was indeed just another planet, as Copernicus had proposed. Galileo made other telescopic discoveries that supported the Copernican model. He observed that Venus went through phases like the moon, full, half, crescent, which could only happen if Venus orbited the Sun, not Earth. He saw that Saturn had a strange, elongated shape, though his telescope wasn't powerful enough to resolve its rings clearly. But Galileo's advocacy for the Copernican system brought him into conflict with religious authorities. In 1633, he was tried by the Roman Inquisition and forced to recant his view that Earth moved around the Sunday. He spent his final years under house arrest, yet his telescopic observations couldn't be unseen. The cosmos had revealed its secrets, and there was no going back. Newton and the force that binds the heavens. Let us drift forward now to England in the 1660 seconds. A young mathematician named Isaac Newton is sitting in a garden, or so the story goes, when he sees an apple fall from a tree. And he asks himself a question that will revolutionize physics. What if the same force that pulls the apple downward also keeps the moon in its orbit? What if the force that governs falling objects on Earth extends all the way to the heavens? This question led Newton to develop his law of universal gravitation. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. It was a stunning unification. The same physical law governed both terrestrial and celestial motion. Using this law and his newly invented calculus, Newton could derive Kepler's laws mathematically. The elliptical orbits, the relationship between orbital period and distance, they all flowed naturally from the law of gravity. For the first time, humans understood not just how planets moved, but why. Newton's Principia Mathematica, published in 1687, gave humanity the tools to predict planetary positions with exquisite precision. The planets were no longer mysterious wanderers, but massive bodies following inexorable mathematical laws. Their paths carved through space by invisible gravitational forces. With Newton's mechanics, astronomers could look at the slight irregularities in planetary motions, the tiny deviations from perfect Keplerian orbits, and understand them as the gravitational influences planets exerted on each other. Jupiter tugged on Saturn, altering its orbit slightly. Earth and Venus subtly influenced each other's paths. The solar system was revealed as a vast, complex, but ultimately comprehensible gravitational dance. The discovery of Uranus, a new world revealed. For thousands of years, humanity had known 5 planets beyond Earth: Mercury, Venus, Mars, Jupiter, and Saturn. These were the worlds visible to the naked eye, known to every ancient civilization that had watched the sky. The idea that there might be more planets, worlds unknown to the ancients, seemed almost unthinkable. But on the night of the 13th of March, 1781, in the town of Bath, England, a musician-turned-astronomer named William Herschel was conducting a systematic survey of the sky with a telescope he had built himself. It was a large instrument, with a mirror 7 inches across, powerful for its time, but still relatively modest. Imagine Herschel in his small observatory, slowly scanning the sky, noting the positions and appearances of stars. He's methodical, patient, moving through the constellations sector by sector. And then he sees something unusual. A greenish disk, distinct from the point, like appearance of stars. At first, Herschel thinks he's discovered a comet. Comets were known to appear disk-like through telescopes, but as he and other astronomers track this object over the following weeks and months, it becomes clear that it's moving in a nearly circular orbit far beyond Saturn. This isn't a comet, it's a planet. A new world. The first planet discovered in recorded history. The discovery electrified the astronomical world. Suddenly, the solar system was larger than anyone had imagined. Herschel wanted to name his discovery Georgium Sidus, George's star, after King George III, his patron. Others called it Herschel. But eventually, following the tradition of naming planets after classical deities, it was named Uranus, after the Greek god of the sky and father of Saturn. Uranus orbits the Sun at a distance of about 19 astronomical units, 19 times Earth's distance from the Sunday. It takes 84 years to complete one orbit. At such a distance, the Sun appears as just a very bright star, and temperatures plunge to nearly -220 degrees Celsius. Uranus was a world of unimaginable cold and darkness, yet it was there, real and substantial, following Newton's laws just like the ancient planets. The discovery of Uranus had profound implications. It doubled the known size of the solar system at a stroke. It suggested that there might be still more worlds waiting to be discovered, and it demonstrated that even in the age of Newton, when the mechanics of the heavens seemed understood, nature could still surprise us. The mathematical discovery of Neptune. Let yourself drift forward now through the early decades of the 19th century. Astronomers are tracking Uranus carefully, trying to refine their knowledge of its orbit. But something is wrong. Uranus isn't quite where it should be. Using Newton's laws and accounting for the gravitational pulls of Jupiter and Saturn, astronomers can predict where Uranus should be at any given time. But the predictions don't quite match the observations. The discrepancies are small, but they're real, and they're growing. By the 1,840 seconds, some astronomers began to wonder, could there be another planet, even farther out, whose gravitational pull was perturbing Uranus's orbit? If so, could you work backward from Uranus's deviations to calculate where this hypothetical planet must be? Two mathematicians, working independently, took up this challenge. In England, John Couch Adams completed his calculations in 1845. In France, Urbain Le Verrier finished his work in 1846. Both men used the observed irregularities in Uranus's motion to predict where an unknown planet should be found. Le Verrier sent his predictions to an astronomer at the Berlin Observatory, Johann Galle. On the night of the 23rd of September 1846, Galle pointed his telescope to the coordinates Le Verrier had specified, and there, less than 1 degree from the predicted position, he found it. A bluish disk that was unmistakably a planet. Neptune had been discovered not by systematic sky survey, but by mathematical prediction. Imagine the wonder of this achievement. A planet had been discovered with a pencil and paper before it was seen through a telescope. The power of Newton's laws, the precision of mathematical astronomy, had revealed a world millions of miles away without anyone having laid eyes on it first. It was perhaps the greatest triumph of theoretical astronomy, a testament to humanity's ability to understand nature through pure reason and mathematics. Neptune orbits the Sun at a distance of about 30 astronomical units, taking 165 years to complete one orbit. It's a deep blue world, colored by methane in its atmosphere, with winds that howl at speeds up to 2,100 kilometers per hour, the fastest in the solar system. But in 1846, all astronomers knew was that it was there, right where the mathematics said it should be. The discovery of Neptune seemed to confirm that the solar system was now completely known. 2 new planets had been discovered in 65 years. Surely that was all there was to find. The solar system extended from the Sun to Neptune, and that was that. Or so it seemed. The long search for Planet X. But even with Neptune's discovery, something still wasn't quite right. Uranus's orbit, even accounting for Neptune's gravitational pull, still showed tiny anomalies. And Neptune itself seemed to have slight irregularities. Could there be yet another planet, even farther from the Sun? In the late 19th and early 20th centuries, several astronomers became convinced that a 9th planet, often called Planet X, must exist beyond Neptune. The most dedicated of these searchers was Percival Lowell, a wealthy American who built an observatory in Flagstaff, Arizona, partly to search for this hypothetical world. Lowell calculated where Planet X might be and spent years searching for it photographically. He never found it. When he died in 1916, the search languished, though Lowell's observatory continued the work sporadically. Then, in 1929, the observatory hired a young amateur astronomer from Kansas named Clyde Tombaugh. His job was to photograph sections of the sky, then compare photographs taken on different nights to look for objects that had moved. It was tedious, painstaking work, requiring enormous patience and keen eyes. Picture young Tombaugh in a cold observatory dome on a winter night in 1930, operating the telescope to photograph the sky near the constellation Gemini. Days later, in a warm room, he studies the photographic plates with a device called a blink comparator, which rapidly alternates between two images. If something is moved between the two photographs, it will appear to jump back and forth while the stars remain stationary. On the 18th of February 1930, Tombaugh is examining plates taken in late January. He blinks between the images, and there, a tiny point of light that shifts position. His heart races. He checks other plates. The object is there, moving at just the right speed and direction for a distant planet. After further observations to confirm the discovery, the announcement is made on the 13th of March 1930, the anniversary of Herschel's discovery of Uranus. The new planet is named Pluto, after the Roman god of the underworld, a fitting name for a world in the distant darkness beyond Neptune. An 11-year-old girl in England, Venetia Burney, had suggested the name, and it stuck. Pluto was a strange world far smaller than expected, with a tilted orbit that sometimes brings it closer to the Sun than Neptune. As decades passed and telescopes improved, astronomers realized Pluto was tiny smaller than Earth's moon. And in the 1,990 seconds and 2000s, they began discovering many other small worlds in the region beyond Neptune, some almost as large as Pluto. This led to a debate that would culminate in 2006 when the International Astronomical Union officially reclassified Pluto as a dwarf planet, a new category for worlds that aren't quite planets in the classical sense. The solar system, by this definition, has 8 major planets, not 9. But let's not get ahead of our story. For now, rest in the knowledge that by 1930, humanity had found worlds extending nearly 4 billion miles from the Sun, a vast expansion from the cozy cosmos known to the ancients. The revolution of planetary science. Through the first half of the 20th century, the planets remained distant and mysterious. Telescopes could show some surface features on Mars, the bands of clouds on Jupiter, the rings of Saturn, but the planets were still just lights in the sky, their true nature largely unknown. Then came the space age. On the 4th of October 1957, the Soviet Union launched Sputnik 1, the first artificial satellite. Suddenly, humanity could place objects in space, beyond Earth's atmosphere. And within a few years, we began sending spacecraft to explore other worlds. Imagine the excitement as the first missions to Venus and Mars were launched in the early 1960 seconds. These were crude attempts by today's standards. Many failed to reach their targets or malfunctioned upon arrival. But in 1962, Mariner 2 successfully flew past Venus, sending back data about the planet's crushing atmospheric pressure and hellish surface temperature of over 450 degrees Celsius. In 1965, Mariner 4 flew past Mars, returning the first close-up images of another planet, a cratered desert world, colder and drier than anyone had expected. The pace accelerated. In 1973, Pioneer 10 flew past Jupiter, becoming the first spacecraft to visit the outer solar system. In 1974, Mariner 10 completed the first of 3 flybys of Mercury, revealing a heavily cratered world baked by the nearby Sunday. In 1979, Voyager 1 and 2 reached Jupiter, returning stunning images of the giant planet, its swirling storms, and its family of moons, worlds unto themselves, some with active volcanoes, others with possible oceans beneath icy shells. Let yourself imagine watching these images arrive, the first spacecraft pictures of Jupiter's Great Red Spot, a storm larger than Earth that has raged for centuries. The volcanoes erupting on Io, Jupiter's innermost large moon. The intricate, icy surface of Europa, hinting at a hidden ocean. The solar system was revealing itself as far stranger and more diverse than anyone had dreamed. The Voyager missions continued to Saturn in 1980 to 1981, revealing the exquisite complexity of its ring system, not a solid disk, but countless individual particles, organized by gravity and resonances into thousands of separate ringlets. They photographed Titan, Saturn's largest moon, shrouded in a thick orange atmosphere. The spacecraft then continued to Uranus in 1986 and Neptune in 1989, giving us our first and so far only close-up views of these distant ice giants. Uranus appeared as a featureless blue-green ball with a strange property. It rotates on its side, its axis tilted 98 degrees from vertical. Neptune was more dynamic, with visible cloud features and that tremendous wind speed. Both planets had families of moons and delicate ring systems. The modern era. New worlds and new questions. Let your thoughts drift now toward the present day, through the decades of continued exploration. Spacecraft have orbited Venus, Mars, Jupiter, and Saturn, studying these worlds in detail. Landers and rovers have touched down on Venus and Mars. The Cassini spacecraft orbited Saturn for 13 years, transforming our understanding of that planet and its moons. The Juno spacecraft currently orbits Jupiter, probing the giant planet's deep interior. We've discovered that Mars once had liquid water on its surface, rivers, lakes, perhaps even an ocean. We've found that some of Saturn's and Jupiter's moons might harbor underground oceans, possibly containing more water than all of Earth's oceans combined. These moons, Europa, Enceladus, Titan, are now among the prime targets in the search for life beyond Earth. We've learned that Venus, Earth's near twin in size, underwent a catastrophic greenhouse effect that transformed it into an inferno. We've watched storms on Jupiter and Saturn, tracking cyclones and anticyclones for decades. We've measured the magnetic fields, internal structures, and atmospheric compositions of all the major planets. And we've made another profound discovery. Planets are not rare. In 1995, astronomers detected the first planet orbiting another sun-like star. Since then, thousands of exoplanets have been discovered. We now know that most stars have planets. The galaxy is filled with worlds, hot Jupiters orbiting close to their stars, super-Earths larger than our own world, and perhaps countless planets like our own. The discovery of the planets isn't over. It has expanded to encompass worlds around other stars, in other solar systems. The question is no longer just what planets exist, but what types of planets are possible, and are any like Earth? And ultimately, are we alone? A meditation on discovery. Let yourself relax now, and consider the journey we've taken tonight. From ancient Sumerians marking clay tablets beneath Mesopotamian skies, to spacecraft sending back images from billions of miles away, humanity has never stopped looking upward with wonder. The discovery of the planets is really many stories woven together. It's the story of human curiosity, the drive to understand our place in the cosmos. It's the story of careful observation, of patient record-keeping across generations. It's the story of mathematical genius, of minds that could look at numbers and see hidden worlds. It's the story of technological innovation, from the first crude telescopes to spacecraft that can function for decades in the harsh environment of space. Each planet taught us something new. Mercury showed us the extremes of heat and cold that can exist on a world with no atmosphere. Venus demonstrated how a planet similar to Earth can evolve in such a different direction. Mars revealed ancient river valleys and polar ice caps, hinting at a warmer, wetter past. Jupiter and Saturn opened our eyes to the grandeur of the gas giants with their immense sizes, powerful magnetic fields, and rich families of moons. Uranus and Neptune, those distant ice giants, showed us worlds where methane ice floats in hydrogen atmospheres, where seasons last for decades. And through it all, we learned about Earth. By studying other worlds, we gained perspective on our own. We understood how special Earth is just the right distance from the sun, just the right size to hold onto water and atmosphere, with a protective magnetic field and a large moon that stabilizes its tilt. We are, as far as we yet know, the only world where life has taken hold and flourished. The ancients thought the planets were gods, or the dwelling places of gods, mysterious and powerful. In a way, they weren't entirely wrong. The planets are powerful, massive bodies whose gravity shapes the architecture of the solar system. And they remain mysterious, even after centuries of study. Each spacecraft mission reveals new surprises, new complexities we hadn't anticipated. The future of discovery. As you settle deeper into rest, let your mind wander forward now, into the future. The discovery of the planets continues. Even now, spacecraft are journeying through the solar system. The Parker Solar Probe is diving closer to the Sun than any previous mission, studying our star and its influence on Mercury and Venus. The Mars rovers Curiosity and Perseverance are exploring the red planet's surface, searching for signs of ancient life. The James Webb Space Telescope, launched in 2021, is studying exoplanets around other stars, analyzing their atmospheres for the chemical signatures that might indicate life. Future missions are planned to return samples from Mars, to orbit and perhaps land on Europa and Enceladus, to send a spacecraft to explore Uranus and Neptune in detail. There's talk of establishing permanent bases on the Moon and Mars, of sending humans to explore these worlds firsthand. And far, far from the Sun, Voyager 1 and Voyager 2, those intrepid spacecraft launched in 1977, have left the solar system entirely. They drift now in interstellar space, carrying golden records with greetings from humanity, images of Earth, and sounds of our world, including the music of Bach and Chuck Berry, the voices of people speaking in many languages, and the sounds of wind, rain, and animals. These spacecraft will drift for millions of years, perhaps billions, long after humanity is gone, long after Earth itself has aged and changed beyond recognition. They are our message to the future and to the cosmos. We were here. We looked outward. We discovered. We wondered. Reflections on cosmic time. Let your breathing slow now, deep and gentle. Feel yourself drifting like a spacecraft through the quiet darkness of space. Think about the scale of time involved in the discovery of the planets. The Sumerians began observing 5,000 years ago. That seems like a long time to us. It encompasses all of recorded history, every civilization, every human story. But it's the blink of an eye in cosmic terms. The planets themselves are ancient. They formed 4.6 billion years ago, when the Sun was born from a collapsing cloud of gas and dust. Jupiter and Saturn formed first, gathering up most of the gas in the young solar system. The inner planets Mercury, Venus, Earth, and Mars accreted more slowly from rocky material. Uranus and Neptune formed later, perhaps migrating outward to their current positions. All of this happened long before there were any observers, long before life appeared on Earth. For most of the planet's existence, they moved through the sky unseen by sentient eyes. They were there, massive and real, following their orbits with mathematical precision, but there was no one to witness them, no one to wonder about their nature. Then, in the most recent fraction of solar system history, life appeared on Earth. Simple cells first, then more complex organisms, then plants and animals. And finally, just a few million years ago, humans evolved. We developed language, culture, civilization. We looked up at the night sky and began to track the wandering stars. In cosmic terms, the entire history of astronomy from the first Sumerian observations to the latest spacecraft images has taken place in less than 1/10,000,000th of the age of the solar system. We are such recent observers, such newcomers to this ancient cosmic dance. And yet, in that brief span, we have gone from wondering what those moving lights in the sky might be, to visiting them with robotic emissaries, to understanding their formation and evolution, to recognizing them as worlds with their own complex histories. The meaning of discovery. As you drift toward sleep, consider what it means that we have discovered the planets. On one level, it's a story of scientific progress, the accumulation of knowledge, the refinement of theories, the development of new technologies. It's a straightforward tale of humanity getting smarter and more capable over time. But on another level, it's something more profound. To discover is to remove a covering, to unveil something that was hidden. The planets were always there, but they were hidden by distance, by the limitations of our eyes, by our earthbound perspective. The process of discovery has been one of removing these veils, one by one, until the planets stand revealed in all their glory. And what have we found? We've found that the universe is larger, stranger, and more diverse than any ancient philosopher could have imagined. We've found worlds of acid clouds and worlds of methane rain, worlds with days that last for months, and worlds with centuries-long years. We've found moons that are worlds themselves, with underground oceans and active geology. We've found ring systems of exquisite beauty, storms larger than our entire planet, volcanoes that dwarf anything on Earth. We've found, in short, that nature's creativity far exceeds our own imagination. Every time we think we understand how planets should be, we discover one that breaks the rules. Every time we develop a theory of how solar systems form, we find an exoplanet system that doesn't fit the pattern. This should be humbling, and it is. But it's also thrilling. It means there's always more to discover, always new surprises waiting. The universe is not a puzzle with a finite number of pieces that we're slowly assembling. It's an infinite well of mystery and wonder, and the more we learn, the more we realize how much we don't know. The ancient astronomers who watched the planets from their ziggurats and temples had one thing right. There is something divine about these worlds, something that inspires awe and reverence. Not because they're the dwelling places of gods, but because they're part of the grand tapestry of nature, the vast cosmos of which we're a small part, the human story. But the discovery of the planets is also deeply human. It's a story of individuals: Copernicus, working in secret on his revolutionary model; Tycho, building his great observatory and making observations with painstaking care; Kepler, struggling for years with the orbit of Mars; Galileo, turning his telescope skyward and seeing what no one had seen before; Newton, unifying heaven and earth under a single set of mathematical laws; Herschel, patiently surveying the sky and stumbling upon a new world; Le Verrier, using mathematics to predict Neptune's position; Tombaugh, examining photographic plates in a cold observatory; and countless others, known and unknown, who contributed to our growing understanding. Each of these people had their own motivations, their own dreams and frustrations. Copernicus was motivated partly by aesthetic concerns. He found the Ptolemaic system ugly and overly complex. Galileo was competitive and eager for recognition. Kepler was deeply religious and saw his work as revealing the mathematical harmony of God's creation. Newton was reclusive and difficult, prone to feuds with other scientists. They were human, in other words flawed, complex, driven by a mixture of noble and mundane motivations. And yet their work transcended their individual limitations. The knowledge they gained belongs to all humanity now. The planets they discovered don't care who found them or why. They simply exist, vast and real, circling the sun as they have for billions of years. This is the magic of science. It's a collective human endeavor that produces knowledge that's universal and enduring. The planets discovered by Herschel and Leverrier and Tombaugh will still be there long after our names are forgotten. The laws discovered by Kepler and Newton will still govern the cosmos when our civilization is dust. A lullaby of worlds. Let yourself drift now, gentle listener. Let the story of the planets become a lullaby, a soft whisper of cosmic wonder carrying you toward sleep. Think of Mercury, scorched and cratered, spinning slowly in the sun's fierce light. See Venus, shrouded in clouds, its surface hidden beneath sulfuric acid mists. Watch Mars, rusty red, with its ancient volcanoes and deep canyon systems, its polar ice caps waxing and waning with the seasons. Drift past the asteroid belt, that debris field of rocks and ice, remnants of a planet that never formed. Approach Jupiter, vast and majestic, with its swirling bands of clouds, its great red spot like an eye watching over the solar system. See its moons, Io with its sulfur volcanoes, Europa with its icy shell, Ganymede the largest moon in the solar system, Callisto ancient and cratered. Float onward to Saturn, jewel of the solar system, with its glorious rings catching the sunlight. See Titan, larger than Mercury, its lakes of liquid methane reflecting an orange sky. See tiny Enceladus, geysers of ice shooting up from its southern pole, creating one of Saturn's rings. Journey to Uranus, pale blue-green, rolling on its side through the outer solar system. And finally Neptune, deep blue, with its great dark spot and its winds howling through methane clouds. And beyond, in the darkness beyond Neptune, the small worlds Pluto with its heart-shaped glacier and countless others, icy remnants from the formation of the solar system, orbiting in the distant cold. All of these worlds exist right now, even as you close your eyes. They circle the sun in their eternal orbits, following the laws of gravity and motion, unchanging yet ever-changing. Ice caps grow and shrink, storms form and dissipate, volcanoes erupt, dust devils dance across Martian plains, lightning flashes in the clouds of Jupiter. The cosmos is alive with motion and change, with processes playing out over scales of time and space that dwarf human experience. And yet we have come to know it. We have sent our instruments to these distant worlds. We have photographed them, measured them, studied them, come to understand them. Rest now. Sleep now, dear listener. Let the story of the planets settle into your mind like starlight on a still lake. You have traveled tonight from ancient Mesopotamia to the outer reaches of the solar system, from clay tablets to spacecraft, from the first questioning observations to our modern understanding of planetary science. You have walked with Copernicus and Galileo, calculated with Kepler and Newton, discovered with Herschel and Tombaugh. You have seen through the eyes of spacecraft the wonders of other worlds. You have participated, in your imagination, in one of humanity's great adventures, the discovery and exploration of the planets. As you drift into sleep, remember that the sky above you holds these worlds. They're there right now. Venus perhaps gleaming in the west as an evening star, Jupiter bright and steady, Saturn visible through a telescope with its rings tilted just so. Mars may be rising red in the east or setting in the west. Mercury might be visible near the horizon at twilight. They're all there, ancient worlds known to our ancestors, yet still mysterious, still full of wonders we haven't yet discovered. And around other stars, uncounted planets orbit, some perhaps like Earth, some utterly alien. The universe is vast beyond imagining, and we are part of it, conscious witnesses to its grandeur. Let this thought comfort you as you fall asleep. You live in a cosmos of infinite wonder, on a planet circling an ordinary star, in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies. You are small, yes, but you are also privileged. You live in an age when humanity has discovered the planets, when we can see images from Mars and Jupiter, when we know that we live in a solar system, in a galaxy, in a vast and ancient universe. Sleep well, traveler through space and time. Tomorrow, the sun will rise, and Earth will continue its ancient orbit, and the planets will continue their stately dance through the heavens. And you will wake refreshed, having journeyed in your dreams through the greatest discovery story ever told. The stars will still be there, waiting, eternal and patient, as they have always been. Good night. Rest peacefully among the planets.